Welcome back. We will begin our discussion on friction on a horizontal surface with a horizontal applied force. In front of you, you have an object of mass m that is resting on a rough horizontal surface. So if we should complete our diagram by indicating the possible forces that are acting on this object, we'll have a vertical force known as the normal reaction R. Let's say this is the applied force that is acting horizontally, and is P. We will have the weight of the object that is going to act vertically downwards. Let's call that W. So if the applied force is acting towards the right in an attempt to move the object, then it means the frictional force have to act in the opposite direction. That is, the frictional force will act on the left. So we call that F as the friction. To repeat myself, so basically we have four forces that are interacting with this body of mass m that is resting on a rough horizontal surface. One of them is the normal reaction that has to be 90 degrees with the surface. The other one is a force that is acting downwards, is the weight of the object. We have the applied force or the pulling force that is acting on the right. So if the applied force is acting on the right, the force that will oppose it will be on the left side, which is the frictional force. We have already stated in our previous video that if no other vertical force is associated with this object that is at rest, then the normal reaction is equal to the weight of the object. So let's begin with that. R is equal to the weight of the object. But we know that weight is equal to mass times gravity, right? So therefore, R is also equal to mg. Okay? This is an important formula to remember. If you have a body that is in a situation like this, and they ask you to find the normal reaction is equal to the weight of the object. So this body, if it is at rest, it is in limiting equilibrium. So if it is not moving, it means that the net force is zero, okay? So if the net force is zero, it means that the applied force and the frictional force are equal, all right? So let me write that condition. At limiting equilibrium, the net force is equal to P minus F, and that is equal to 0, okay? So because it is not in motion, so we can say P is equal to F, okay? The net force is 0, and at equilibrium, the applied force is equal to the frictional force. Going back to the diagram, if you have a frictional force of a certain magnitude, then you need an equal force that is going to act in the opposite direction for the object to remain in equilibrium. Okay? But the frictional force F is equal to mu R, where mu is the coefficient of friction and R is the normal reaction. Therefore, one can say the pulling force P, also called the applied force, is equal to mu R. And we already know that R is equal to mg, so therefore the pulling force is equal to mu mg. So this P will be the force required to keep the object in equilibrium. That is, the body to be at rest. Okay? So what if the body is in motion? The body is in motion. That is, it is accelerating. So there is acceleration. So which means the net force cannot be equal to 0. Okay? It is important to note that if the body is in motion, then the net force will not be equal to 0. So it means the applied force must be greater than the frictional force if at all the body is to move, right? So the net force will be equal to P minus F. So that is equal to, according to Newton's second law of motion, the net force is equal to mass times acceleration. So P minus F is equal to ma is an important formula to remember when you are dealing with a circumstance where there is acceleration. Using this, we can substitute for the parameters that we have already derived. P minus the frictional force is mu R. This is equal to ma. So P minus mu, R is not affected, so R is still equal to weight, okay? Why? Because even if the body is accelerating, the vertical component is not affected, so which means the R and W will still be equal, and W is equal to mg. R is mg, that is equal to ma. So we can say P is equal to, if I take this negative mu mg to the other side of the equation, I will have positive mu mg. So that is mu mg plus ma. Okay, the pulling force is equal to mu mg plus ma. So if you can remember this formula, it will be very important for you, because you can be asked to calculate the applied force or the pulling force. You can be asked to calculate the coefficient of friction. You can be asked to calculate the acceleration. And it's even possible they ask you the mass. So remembering this formula is very important. Now let's say we want to calculate the coefficient of friction. So using P is equal to mu mg plus ma, then I can say P minus ma is equal to mu mg. So to make mu the subject of the formula, I will divide both sides by mg, and therefore mu is equal to P minus ma all over mg. All right, so this is the formula for the coefficient of friction in a circumstance like this. But mg is the weight or the normal reaction, so we can also say that mu is equal to P minus MA divided by the weight, or mu equals to P minus MA divided by the normal reaction R. So let's say we want to find the acceleration. All right, so the acceleration using the formula P is equal to mu mg plus ma, then P minus mu mg is equal to ma. Then to find the acceleration, I have to divide both sides by m, and therefore acceleration is the pulling force minus mu mg all over m. Okay, that is all for this lesson. In our next lesson, we will solve problems of frictional force on a horizontal surface. Thank you very much for watching this video. Please subscribe to this channel, like and share the video.